Hello, my friends. Let's continue our conversation from the last PowerPoint talking about ln's to start to discuss e. E is a very special number in mathematics. It's much like pi. It's irrational. It goes on forever without any kind of pattern. But much like pi, it creeps up in a lot of spots in math, so much so that we decided to give it a name. I don't know why they picked E. It could be the fact that the mathematician who discovered it, Euler's name started with E, and maybe he just wanted to keep that namesake going on. I don't know. But E pops up all over the place, from the curvature in a conch shell, if you're listening to the ocean, to the seeds in a sunflower, to the ridges on a pine cone. It pops up all over the place. And that's why we refer to it as the base of the natural log. Also check out this really crazy equation. E to the pi I plus 1 equals 0. It's kind of insane that three of these crazy important numbers in mathematics fit together so nicely in this simple equation. Alright, so let's try and use this bad boy. If you've got a natural log problem and you want to get the y out of the natural log, essentially you just want to use your log skills to rewrite this. Remember that this ln is essentially log base e. So my rules are I take the base to the far side equals the near side. And that's my statement. I now have y in terms of t. I don't have to say y in terms of t and e because e is a number, much like pi. You don't have to list it as in terms of. T is my variable. So if I know a t number, I can plug it in, raise e to that power, and get my y. Alright, so let's play around a little bit with graphs. For natural log, we took a look at what happens when you graph the antiderivative of natural log, and we came up with an equation. So let's take a look at the antiderivative of e to the x. The antiderivative of e to the x has a curve. It has this kind of growth rate, just like some of the other guys. And I'll leave you to think about whether that looks like something you've seen before. Hopefully you thought about it, because now we're going to talk about it. If I move that starting point from A to B, and I draw it again, it just so happens that e to the x has the remarkable property that it is its own antiderivative, meaning the integral of e to the x is simply e to the x. Whereas Euler noted, the integral of e to the x dx equals e to the x plus c. You know, just to give you an idea as how crazy smart this guy was, he was asked later in life to see if he could come up with the math to predict navigation for ships. Due to some medical conditions, he ended up going blind. While blind, he still worked out the math for navigation by dictating it to a scribe. Imagine being able to do all your math in your head and then being able to say, whoops, I made a mistake. Go back 3 steps, change that 3 to a 5, and let's continue. The guy's hardcore smart. Alright, so here we get to try it. My integral from ln of 2 up to ln of 3 of e to the x. So that's going to be e to the x, evaluate it from ln of 2 to ln of 3, which is e to the ln of 3 minus e to the ln of 2. Remember my log tricks. E to the ln just cancels each other, so that's just 3. These cancel each other, and that's just 2, and my final answer is just 1. So the area under e to the x between these two stops is just 1. Similar story, slight difference in this problem. The last problem was just straight up e to the x. This one is e to the negative x, which means I need to adapt it a little bit to kind of fit my formula. What Euler might have actually written was e to the u du's integral is e to the u plus c. So I need to pick a u. And now we get our last location of u. U loves to hide in parentheses, u loves to hide in the denominator of fractions, and u also loves to hide in exponents of e. So my little side derivative is pretty easy here. And I get dx equals negative du. So this integral is now going to become 0 to ln of 3 of e to the u times negative du, or negative e to the u plus c. That negative just comes along for the ride. Once I've taken my integral, I'm going to swap back out my u. It's really opposite of x, and I want to evaluate that between 0 and ln of 3. I plug an ln of 3 in there, and again, be very cautious. I'm sorry, I don't need that plus c. When I plug that ln of 3, I can't cross out the e and the ln the way I did in the last problem because that minus is in my way. One solution to that is I can bring this minus up as an exponent inside the log, and now it's e to the ln of 3 to the negative 1. Once I make that move and there's nothing in between my e and my ln, they now cross out. So I get negative 3 to the negative 1. When I plug a 0 in there, it's going to become plus e to the negative 0. Like, you can really make 0 negative. E to the 0 is just 1. So now I'm going to get negative 1/3 plus 1 to become 2/3. And I've got an answer. Again, we want to think about all the things we know about substitution. I don't have a product rule, so that's out. I could either let this inside be my u and then see if I can make stuff cross out, or quite simply just distribute in. I think distributing in is probably a little bit easier. E to the x times e to the x is going to be e to the 2x. So my integral of e to the x is just e to the x. My integral of e to the 2x, I'd have to do substitution, let my u be 2x, and realize along the way I'm going to pick up a 1/2. E to the 2x evaluated between 0 and 1. So when I plug a 1 in there, I get e plus 1/2 e squared. When I plug a 0 in there, I get e to the 0 plus 1/2 e to the 0. Remember, anything to the 0 power is 1, so this is going to become 1 plus 1/2 or 3/2, and now I have my answer. Similar story, I'm going to pick a u because it's too hard to do just straight up. My u loves to be the stuff in the exponents of e's, so I'm going to get a negative 2x dx. My dx is going to be du over negative 2x. Pretty convenient because that 2x out front is now going to cross out with this 2x I'm putting on the bottom. And again, I pick up that negative. So my integral is just going to be negative e to the u, or negative e to the negative x squared evaluated between negative 1 and 1. I plug a 1 in there, and I'm going to get negative e to the 1. Negative 1, because the square happens before the negative. And then when I plug a negative 1 in there, I'm going to get the same thing, plus e to the negative 1. So this whole thing's just going to come down to 0. All right, so again, at first glance, there's no fraction way to kind of split this stuff up, so I have to think about my u's. I need a substitution trick here. I don't want to pick a power of e to be my substitution because that's not going to make anything cross out. So I go back on my list. I've also got things in parentheses or denominators of fractions. I just so happen to have a fraction, so I'm going to pick that to be my u. So my du, remember the derivative of 1 is just gone. The derivative of e to the x is e to the x. And this looks pretty fruitful. So I've got the integral of e to the x over u times du over e to the x. What do you know? Those guys cross out. And I'm left with 1 over u du. Think to yourself, what is the integral of 1 over u du? We learned that earlier in the chapter. We know that that is the natural log of the absolute value of u plus c. I do need the c here because I don't have a's and b's. But u is really 1 plus e to the x. I would love to say that ln and that e cancel each other out, but that plus sign is blocking me from doing that. All right, so then we hit this problem. Extremely similar to the last problem, but with one slight difference. It doesn't have that e to the x up top. If I try and pick a u in this problem, it's a dead end on every path. The exponent's not going to work, the denominator's not going to work, I don't have any parentheses, so really nothing is working. Which means I need our friend, Wolfram alpha. Now for this problem, I could either just type in 1 divided by, I think it was 1 plus e to the x, and I can analyze that graph. Or Wolfram can help me out even more by saying integrate. If I integrate that, then I get x minus log of e to the x plus 1. So there must be some kind of a way to pull that off that's beyond the scope of what we've learned. Notice in Wolfram that when they say log, they're actually referring to the natural log, ln. So if you ever hit a problem that seems like there's no way to do it, you can attack it with Wolfram. It's not going to help you much on a test, but it'll help you a lot with homework or possibly in college. All right, so let's just review a little bit of what we learned in the last chapter, playing around with the idea of volumes. So y equals e to the x, which you saw before, that's going to be some kind of a graph like this, between 1 and 3. So that's our shaded region. And we want to go about the y-axis. So where you're rotating that region around is going to make a big difference into which technique you pick. Because we're rotating around this axis, and yet we're shaded up and down, it makes a lot more sense to approach this as a shell. So I want to approach this as a shell dx. If I'm approaching it as a shell dx, then I'm going to have 2 pi, the integral of stuff and stuff, dx. So the first thing is my radius. My radius going from this point on the inside is just x. My height in this case is just a function, so that's e to the x, starting from 1 to 3. Well, the fun part here is, honestly, I don't know how to approach x times e to the x because it's not going to fit any of our formulas. Substitution won't help me. So this would be a good time to either go to Wolfram or go to FN on your calculator, and then I could produce the answer for you. Hopefully this made a little bit of sense, and hopefully you're getting a better sense of how ln's and e's interact with each other in the world of calculus.